and the transcription. So this morning I did RMS and a little bit of op-amp. The video from this morning has already been posted. And where would that be? I'll show you in a second. But it's the same Google Doc links that I gave you in class the other day. But right here, these are the, if you go there, you can see the video session for this morning. So actually, I thought it might be more efficient rather than just repeat what I said, but to go over other things. And RMS, right, is although important, is somewhat an independent topic. And I thought I would kind of start with op-amps. Okay. So I kind of wrote some things out ahead of time. And again, I'll share this video. These notes are kind of not easy to share. Like I can't just make a PDF of everything, so I don't really share them. But I do have a whole review course in my open math that you can look at. So I believe, oops, if we go to 110, we click on accessing the homework after the due date. Okay. So that's actually, you can get into the My Open Math shell after due dates, and just for practice, it doesn't count. But what I thought something else was there. I'm going to show you that I actually have a whole online EE98 course . Here. And sorry to do this live. I thought I'd had it done. I have a lot of information squirreled away in a lot of different places. Okay, so if you went to my open math, there's EE98 practice, and there's every module with homework assignments and notes, right? Of course, you don't, while it's all important, not every single skill in 98 is used in 110, right? But there, that's just some more information, right? And the other thing, just to re-point out, is in 110, you have the midterm practice and the review. Okay, this is the first problem. I actually have a help getting, get like a 10-minute video on calculating RMS, okay, which it's already right there. The other things don't, or at least they don't yet, or they're part of like much bigger videos. All right, so just trying to get everything out of the way so I can see. So what I thought is starting with op-amps, okay? Now, op-amps are used to take a signal and perform a mathematical operation on it. Now, the mathematical operations you're most used to are multiplying it by a positive number or multiplying it by a negative number, right? However, op-amps, if configured properly, can integrate, right? They can take the natural log of something. They can integrate more than one signal. They can sum more than one signal. They can convert current to voltage. So if you had a photodetector that was giving a current based on a light source, the op-amp can take that current and convert it into a voltage, right? So there's a lot of things that an op-amp can do with analog signals, right? So that you can then input it into a microcontroller for further processing, right? So you can do a lot of things with an op-amp, but microcontrollers can be much more flexible and easier to implement functions, but it's really not a case of one or the other, right? Use a microcontroller and just take an analog to digital converter and then process everything on a chip, on a digital chip, right? Because actually the analog to digital converter needs an op-amp filter kind of in there somewhere, all right? So they're really important, okay? And in 110, we're going to continue the conversation from EE98. 122, you'll learn even more about op-amps. And even in EE 124, you'll learn what goes on the inside of an op-amp. All right. So anyway, but let's start with analyzing an op-amp. All right. So what I wanted to do is say, make it more generic, right? We have our V minus here, input, our V plus input, and this is just our out, all right? And in fact, this op-amp is a behavioral voltage source where you take something called the AV, which is open loop gain, and all that means is gain just means take a signal and multiply it by a constant. And yeah, the constant doesn't have to be positive, and it doesn't have to be greater than 1 even, right? So this is actually a behavioral voltage source, ideally. And an ideal voltage source can drive any current or sink and source any current. And that means supply or receive any current. And then to keep it more generic, rather than the resistors you might be more familiar with, I'm just saying Z1 and Z2 impedance, right? And what I want to do is derive a relationship that then you can use to easily, in a much quicker way, analyze everything else. All right. But yeah, we consider the op-amp to be ideal. That means the input resistance is infinite and these currents coming in are zero, right? And V out can be any value and it can, receive or sink. All right. So in this circuit, I just have this node. It's not really connected. I'm just calling it V plus. But this node, yeah, I'm calling that in, that's out, and Vx is right here. All right. So if these currents are zero, then there's only one nodal equation, Vx, because V out depends on V in. So there's only one unknown. Once you know the difference between these two voltages, then you know V out. So we have the current of Z1 equaling the current of Z2, because this branch here, we said it's ideal. Zero current. Now, is it really zero? No. But if these two currents are 100 times bigger than that current, then it's effectively zero, right? So we just set those equal to each other. I assign the current directions and the voltage drops, and V in minus Vx divided by Z1 equals Vx minus V out divided by Z2. Okay, fairly straightforward. Now, yeah, we have two unknowns, Vx and V out, but V out depends on Vx. So we just substitute this equation right here, right? That's that open loop gain I talked about, which we will ultimately in this analysis set to infinity. But in 110, it is not always infinity. But for today, we can call it that. We have V plus minus Vx. And we just substitute that in there. We get this equation, right? Now, what I'm going to do is let these open loop gain go to infinity. So if this is going to infinity, then this is being scaled by infinity. If AV is, again, if this is going to infinity, then this is being scaled by infinity. And this is getting bigger and bigger, and everything else, well, is going to zero, right? So we really get 0 over Z1. I'm just going to scroll a little bit. Right? So since this isn't scaled by infinity, this isn't, or sorry, V in isn't scaled by infinity, Vx isn't scaled by infinity, this whole term is going to 0 in comparison in the limit, right? This isn't scaled by infinity, so it goes to 0. So we're left to 1 over Z2 equals this, right? And ultimately we get the open loop gain times V plus times the open loop gain times Vx scaled by 1 over Z2. Well, you can see that these cancel out. And this is the important result. V plus equals Vx. Or should I say, these two voltages, these nodal voltages, equal each other, all right? Now, do they really equal each other? No, but they can be within several microvolts of each other. Now, there are times when they're not equal to each other, right? When used in a comparator, or when the op-amp is no longer behaving in an ideal fashion. Now, that is a EE 110 subject, right? But like I said, for today, these two things are very close to each other, okay? So if the op-amp is ideal, and there's a current path from out to in, and there's a way for Vx to depend on V out, meaning feedback, right? Then we can say these two node voltages are equal to each other, which then will make everything a lot easier. Okay. So now let's do an analysis. Right, here is the inverting architecture. Here's my Vx. And now instead of V plus, I'm tying it to ground, right? V plus is equal to 0. Now from before, ideal op-amp, there's feedback here, right? V plus equals V minus, Vx ultimately now equals 0. So when I write that nodal equation, right, Vin minus Vx divided by Z1, Vx minus V out divided by Z2, well, now I can say Vx is very close to 0, right? And then we can just solve for it, and we get V out over V in. In 98, or your circuits class, it might have been called gain, G, but in 110, we're going to call it H of S, transfer function. And the reason is these impedances can depend on S, right? So ZC is 1 over SC, ZL is SL, and S is J omega, the frequency, which means we're in the frequency domain. We're using sine waves or a sum of sine waves. So that S is just a shorthand way of doing it, because S is from the Laplace transform, but a lot of the math is the same. It's just a few of the assumptions are different, but it can have big implications, but on a day-to-day basis, sometimes you forget which one you're using, Laplace or Fourier. All right, well, now let's do the non-inverting, right? Z1, Z2, right? I assign my current directions, my voltage drops. Again, this is a behavior voltage source that depends on the difference between these two signals. So this is an input, I know it. Vx is the thing I don't know. So it's one nodal equation, right? 0 minus Vx divided by Z1. Vx minus V out divided by Z2. But now instead of Vx equaling 0, it equals V in. Substitute that in, manipulate the math, and we get our classic non-inverting gain stage equation. Okay. So sometimes you have to analyze things that way, but in 110, you will just start to remember these two fundamental things. And you're going to be designing bigger systems where you can't do a nodal analysis on a circuit with 4 op-amps. You're never going to finish. All right. So as an example of that, right, let's do this circuit. Okay. So I have an input here, right? I have the output here, but I have 2 op-amps in series, right? So really, it's quite easy. I recognize, right? There's an op-amp. I'm going to assume it's ideal. I have R2 and R1, right? And I can tell by looking at it that this is the V1 equals minus R2 divided by R1 V in, right? Now you might say, hey, what about R3? Well, if this is ideal and it can source or sink any current into R3, right? If I say I have an ideal battery or an ideal voltage source, right? If it's ideal, it can put it will supply the current needed to make the voltage VR equal to V in, right? Because it's ideal. Now, non-ideal might have a series resistance, and then it gets a little tricky, right? But anyway, in these analyses, you assume the best until it doesn't work. Or in designing, you assume ideal because that's easier. Then you add in effects to say where it's not ideal. So really, that's all it is. And by the same token, I recognize this, right? That's an inverting op-amp stage, except its gain is minus R2 over R3. Okay. Well, if V2 equals minus R4 divided by R3 times V1, all right, what's V1? V1 is minus R2 divided by R1 Vn. So substitute this into here, we get V2 minus this factor times minus that factor, and we get R2, R4, R2, R3, R1. Okay. So that's, you might call them cascading. Those circuits are in series.
And Professor?
Yes, sir.
For R2 over the V out, the final V2, we're missing a V in there, right?
I think it went off the page.
Okay, yeah. I see. But it is. Okay, got it.
Yeah. Good catch. So we can now do pretty complicated things, right? I have circuits that might have 4 of these in a row, right? And you'll learn about them in class later as the semester progresses. So now, yeah, we have an inverting stage, and we rapidly came up with an equation where we just remember this and we remember that, and now you just have to multiply them together, right? I don't derive this out any time by now. You just work with it so much that you know what it is, okay? I only mention it is because sometimes on exams, people are trying to solve 110 problems, what I might call the EE98 way, which there's nothing wrong with, but it takes so much time, you kind of run out of time, all right? So like a painter has all these paints on its palette, right? And a painter isn't wondering where does red come from. He's just painting with red, right? She just chooses yellow, whatever. Okay. So now we can get even to even a different circuit, right? Where I have this stage and this stage, but now I have a ZC. Well, here's the thing, and this is going to be the beauty of using impedance, right? And just as a refresher, S equals J omega in this case, right? When we calculate certain things, sometimes we just leave it as S, okay? But remember that omega is like a phasor, right? You just choose one frequency, it exists forever, right? But the Fourier, we can have any frequency we want, okay? And these sine waves exist for all time. So I know this, right? I remember it from the last slide. Okay, minus R2 over R1. Here, right, remember it was kind of Z2 over Z1. Z2 of a capacitor is ZC. This Z is just R. So I get 1 over SR3C. And there should be a minus sign there. Well, again, I just multiply them together. Okay. Now, this S, now I'm going to say it's the Laplace, it's the Laplace function. I know in differential equations, you talk about the Laplace transform. maybe not so much about the inverse Laplace transform. But if I take the inverse of this, these are all constants, so I put all constants here, right? This 1 over s turns into an integration, okay, of whatever the Vn happens to be, okay? So that's pretty much all you gotta, that's it right there. Now, just so you know, in order to get my open math to do that, like let's say this was going to be integration, instead of this integrate symbol, it can't do. So I've set up a variable called int, and that's integration. And it will make sure it'll check if your answer is correct, right? So again, if you come up with an answer with a integrated a Vn dt, and we're not really worried about the limits, right? You would just type in a times int. That int would be the integration symbol, Vn, and it's case sensitive. And dt is another variable, right? So, you can figure it out, right? And just as a reminder, you're just answering the answers here on your own, so you can get rapid feedback. I'm not actually checking your work on exams, though. Actually, exams are gonna, besides that exam, they're all gonna be hand graded, so you don't have to worry about it. But I've given you like enough chances if you make a typo or something like that. All right. Now, if you're not too firm on the Laplace transform bit yet, that's okay. There's another way to do these problems. So we keep it in the time domain. So I assign my currents, right? And so this current, IR1, it's the same thing. Vn minus Vx divided by R1, right? But now this current is really C times a derivative, right? I can't really, in the time domain, take something of capacitance and divide it by something of resistance. However, I'm saying the op-amp is ideal. I'm saying there is feedback, right? So I can say these two things are equal, these two nodes, and so Vx is 0. Well, if Vx is 0, okay, then we get Vn over R1 equals C dV out dt. Solve for V out, and we get 1 over R1C integration V in d time derivative. Okay, so you can do it in the time domain, right? And we can even do circuits with diodes. So, a diode curve kind of looks something like that. And at each point, right, there is a resistance, but there's no way to ensure that you're at any given point with Vn, right? So it's not linear. You can't just say something of diode divided by R, or minus. Oh, and I'm sorry. There should be a minus sign. What happens is that when you use these in larger systems, you can invert that minus sign very easily. Okay. All right. So we set up our KCL. We have our voltage drops, right? IR1 equals ID for diode. Great. This is an ideal op-amp. There is a way from V out to communicate with Vx. So V minus equals V plus equals 0. Right? So that's something we just use time and time again. Now remember though, if this was equal to V in, V minus would equal V plus would equal V in, right? You can't just say that node is, oh, this is always 0. You can't memorize that. It's just these two things are equal to each other if it's ideal and if there's a way to communicate. All right. V in minus Vx divided by R in. Now, what is this? In the forward bias, there's something called IO, and it's a scale factor, and you'll learn about it in MATI 153 and EE 128. VD is the voltage drop across the diode, and there are some scale factors, which these are just scale factors. Today's not, and they take a bit of device physics to find out what they are. Okay, so I don't want to distract from today. Well, what is VD? The voltage across that diode is Vx minus V out, right? Well, rather than write it all out, I want to kind of take a shortcut. If these things are equal to 0, right, then that's 0. And so this is 0. All right. So we have V in over R. Actually, I'm not going to call it in anymore, just R equals I naught e to the minus V out, ideality factor, and thermal voltage. Right, so okay, and so now V out is dependent upon the log of V in. Okay. Oh, sure, there's some scale factors here, but you can use this, right, to multiply two signals together, right? I can have one signal where I do take the natural log of it, another signal where I take the natural log of it, add them together, and then take the inverse log, and I'll have multiplied my two signals together, right? But this can also be used in compression circuits, sorry. So if you well, I guess I have it on Wikipedia. but I'd rather work with analog devices today. So, you know, they go through this derivation of all of that, right? But this, using this BJT like this actually makes a better circuit, which I'm not going to go into today. But so the AD538 monolithic, meaning one chip, analog computer which can multiply, divide, and raise powers, right? And it's all based on that. Okay. So a computer to calculate that, where is the series, Taylor series, clone series, where's the, you see, you end up doing all these multiplications on your chip and scaling and dividing. Now you can make a lookup table ahead of time, right? There's a lot of tricks to doing that digitally, but even though doing this digitally is the predominant paradigm, analog still makes a lot of money selling analog multipliers. Okay. So that should get you through this problem. Okay. But that's a lot of information. Okay. Are there any questions? Okay. So I basically I'm putting an initial condition. V1 at time equals 0 equals 1 volt. Okay. So I want to know how this is going to evolve. How is V1 going to evolve in time? Right. And yeah, just so you know, I can put an op-amp here. Right. And so whatever V1 is going on here, V out is going to be multiplied by some positive number. Right. But that's not what we're about today. Okay. So there's kind of the differential equations way of doing it. And there is the Laplace transform way of doing it. All right. And the kind of quickest way is in the time domain is we're not going to worry so much that it's 1 volt at the beginning. All right. But what can trip people up are the currents directions, right? So these are all on one mesh, right? So I can do it in mesh style or KCL style. But basically, as drawn, right, IC equals IR, right? And again, now this is going to be nodal analysis, all right? But if I put the symbols here, plus minus, right? Well, the node voltage of 1 is measured with respect to ground. And so VR, right, is equal to V1 to ground. Okay. In nodal analysis, everything is mentioned with respect to ground, but we might just say V1, right? But V1 isn't V1, it's with respect to something. What's missing is the ground symbol, and you just don't mention it. Okay. But VC, right? Well, what's VC? I put the current direction here. It's plus minus, right? Because the plus goes here and the minus goes there. But according to the nodal relationship, V1 equals minus VC. And so that can really trip people up. Okay. So now, so IC again, this is a nodal equation. So IC is 0 minus V1. But again, in the time domain, this doesn't have an impedance that we can just scale. So what do we have to do? We have to do, well, that's the derivative in time. And then we have the capacitance, right? And I just got done saying I haven't forgotten about that. And what's R1? That is just V1 divided by R1. All right. So now let's just rewrite this over here. V1 R1 equals minus and in fact, it's not just dV, it's dV1, right? So now I have a negative of something, right? So the derivative of the negative of a derivative of the function equals the function itself. What's the only thing that can be? From differential equations. Right. If V1 equals a sine wave, does the derivative of a sine wave equal the minus of a sine wave? Does the derivative of a cosine equal the minus of a cosine? Arctangent, x squared, any of that? No, it's the only thing that does that is e to the minus t, right? So they make a big deal out of it, but really, you're just guessing functions that work, right? So really, V1 equals 1 over R1C e to the minus V minus my bad. Okay. Now, I just want to erase something. Okay. So here's the thing. I don't really know what A is, right? But now I use my initial conditions. Well, my initial condition was 1 volt, right? So there's no power source here. So I have to start at a volt, at least the way this works, right? Otherwise, there won't be any solution. All right. So then we just get 1 volt e to the minus t RC. Okay. So now how that initial condition gets there is not for today. Okay. So it's going to have this relationship. All right. So if that's 1 volt, how long does it take to get down to 0? Right? Well, we have an approximation of 5 tau, right? So let's look at our decaying exponential, right? We're going to call R tau equal to RC. It's just a time constant, all right? And we're going to say that if T equals 5 tau, which then would equal 5 RC, then e to the minus 5 RC divided by RC equals e to the minus 5, which is really close to 0, okay? And so drawing this shape, and also it can go up like that, and labeling that 5 tau is something you're just going to see again and again and again on job interviews and things like that. All right. So when you see a circuit like this, right, you know that it's got to be exponential decay, right? If I put a signal here, eventually if I put a charge on this capacitor, eventually it's going to decay through that resistor and go to 0, right? And based on the differential equations, the only thing that can be is a decaying exponential. Because if it was positive, it would increase. Where's the power coming from, right? We just stored some energy on that capacitor. You can't get more than you put in. So now, yeah, there's so if I had this circuit, R1 and R2, well, it's really just e to the minus t. The c is the same. But that R is just really R1 plus R2, right? The equivalent, right? If I had this problem, right? Well, again, it's e to the minus t. The C is there, but now what's the equivalent resistance? It can discharge through here, discharge through there. R1 parallel with R2, right? And yeah, this is where things can get tricky in circuit design. I can have this, and I can have that, right? Well, mathematically, this circuit and that circuit is the same, right? From a nodal standpoint, there's no distance here. It's all one point. So it doesn't really matter whether they're over here where it might be easier to see they're in parallel, or they're split apart where it might be harder to see, right? This will be the time constant is really, even though now they're out of order, it's the same. Now, what is VC? It's not going to be the same VC here, V1, because in this case, V1 is across the capacitor. I'm sorry. In this case, V1 is between the capacitor and the resistor. Here it's between the resistor and the capacitor, right? Or I could label this V1, right? It's not the same. But so the scale factor would be different, but the time constant is the same. All right. Now, this too can be done in the Laplace or the impedance method. Call that ZC and Z1 or ZR, just R for now. This just, so now I just put it in the impedance domain, but then there's also the initial condition. Okay. So now this might look maybe a bit weird to you at first, but this initial condition, pretty standard way of doing it, because we kind of just assume that that initial condition appears at time equals 0. We just do it divided by S. But this is still my node 1. Now let me redraw that, right? This is V naught divided by S, right? So now that's our 1 over SC. So this here, this node is that node. And this is the node V1, the one we wanted, right? And really, now if this is the input, I can just say it's in or initial condition, right? V initial condition divided by V1 is just voltage division. Which when you take the inverse Laplace of that, you get that decaying exponential. Okay. But probably, I'm just telling you, that's kind of like the future of where we're heading. The way I do these problems is let's just say I kind of puzzle it out, right? Okay. So in this case, we're saying V2 equals 0. Okay, so that's our starting, right? How is V2 going to go in time, right? So you see an RC circuit here, right? You know when this switch closes, there's going to be a current flow, right? The battery is going to supply current through the resistor, and V2 is going to charge, right? Right now and so it's an RC circuit. So somewhere in the final equation, we have to have e to the minus t, right? And because it's a RC circuit and there's one, when it's closed, I go through one R and one C, it's just going to be that, okay? Now, where that's at the heart of it, but we don't quite know where we're at yet, right? So now we're actually going to use the impedance a little bit in our analysis. So this is time, this is 0, and this is, you know, a long time. All right. So we said, hey, it's at 0. Okay, when we start. All right. Well, what about a long time after that switch is closed? So let's draw the circuit with the switch closed. Okay. Well, if this switch closed for a very long time, right? This, we're saying it's charged, but at some point it'll reach a maximum and stay constant, right? So after a long time, V2 looks DC. Thus omega equals 0. Thus ZC equals 1 over 0 equals infinity. Well, if this is infinity, right? Let's just erase it. It's not there. So no current can flow. So there can be no voltage drop. So V2 equals V1. Right? Right? Which we said was 1 volt. Okay. So we started off at 0. We're here at 1. I know that this is in there somewhere, right? How do I figure out what the full equation is, right? Because is it going to do this? Is it going to do that, right? How can we figure it out? Okay, so we just say V2T. It's going to have some, call it a constant value, plus some scale factor, e to the minus t RC. I just don't know what these are yet, right? And just a quick sketch. At 0, we're 0. And I'm just saying right now, long time, I'm at 1, right? So V2 at 0 equals VA plus VB e to the minus 0 RC. And that's supposed to equal to 0, right? So this turns into 1. And so we have VA plus VB equals 0. And we get VB equals minus VA. All right, so that's one condition. All right, well, what about a long time? Well, long time is 5 tau, or time is greater than 5 RC. So V2, T greater than 5 tau, right? We still have our VA. I can substitute the fact that VB equals minus VA right now. That's minus 5 RC divided by RC, which brings this whole thing equal to 0. From the rough graph, right, we said it's going to be equal to 1. And so VA equals 1. VB equaled minus VA, so that's minus 1, right? And now we have V2. 1 minus 1 e to the minus. Okay. Now, yeah, t less than 0, V2 of time equals 0. We have a way of doing that in 110, which I'll tell you about in class. All right. So now, yeah, we can sketch it out. Right? There's t. I go from 0 to 1. I have this. It takes 5 tau, whatever RC is, and that's how long it takes to get up there. Okay. So that's, you know, pretty generic thing. If we look at okay, that's like the first one. Here's the one where I said they're in series. Here's the one where I said now these are in parallel. And now I have these are in parallel, and it's just multiplied by the gain. Okay. Now that's so the RMS one, right? I have a 10-minute video. You can read about it. You can see it from this morning. The op-amp one, right? It's oh, I think I did it. Oh, I meant to do the other one. And then you have an inductor. But again, that's just SL, or you just have to use the time domain equations of an inductor, right? But really, this is just a decaying exponential. Tau equals RC. Tau equals R1 plus R2 times RC, parallel combination times C. Tau is the same here because if this is an ideal op-amp, no current flows. It all discharges to these two resistors. Okay. Now, yeah, other things are the RLCs, which I was thinking of making little mini videos just to kind of refresh your memory on that. And yeah, there's name that filter, which we're actually almost ready to talk about. Okay. But, you know, in a sense, that's a long class. So probably people are already dropping off, you know, thinking they're going to watch it later. Right. Probably what'll happen is they'll try the homework and then maybe look at the videos, or maybe they already know it. So we'll see. Any questions?
Thanks, Professor. Disregard my email about problem number 3. You just explained it pretty well, so I think I can do it now.
Did I? Oh,
I think I sent it to you right before the
that's all right.
meeting.
Yeah, yeah. You know, I don't. Sometimes I can't always get to them. So if you don't hesitate to send me an email, right? However,
I know.
if all of a sudden you answer it yourself before I get to it, yeah, send me another one. Hey, no worries. Because then I'm happy. I'm like, oh, you figured it out yourself.
I haven't figured it out yet, but you went over it, so
okay,
you covered it, so it's good.
All right.
All right.
All righty.
All right. Thank you.
Fantastic. All right, guys.
Thank you.
Have a good day. Have a good weekend. Take care.